Right. So today we are going to continue with the continuous groups, and I put up some notes. So the things we wish to now talk about are the continuous groups. So last time we talked about continuum, okay. Groups. Last time we began with discussing about what is the continuum. So we need a set, and we need to understand what is meant by a continuous set. Very roughly speaking, any set parameterized and this is of course a special word, by a set of real parameters. We will temporarily call them something x1, x2, xn. We are just using the Cartesian notation. In other words, a set that has one-to-one correspondence with Rn. So last time what we tried to do was actually discuss in what sense in what sense the real line itself is a continuum. So fundamentally, if you accept that the real numbers form a continuum, everything else that you can put into one-to-one correspondence with it is a continuum. But why R itself forms a continuum has had a very difficult intellectual history. Now we take it all for granted, but it is a important history. So by why we mean in what sense? Mathematical thought. Okay, so it's not philosophy as in philosophy, but actually mathematics. So this we went over last time, essentially saying there is a progression from fractions which do form a set such which looks like you can always find a new fraction between two existing fractions. Between two integers you can't find a new integer always, there is only a next integer or a previous integer. But given two fractions and just focus between 0 and 1, even the fractions between 0 and 1 have the property that between any two of them there is a new one. Okay, so because you can take sum of the two and divide by 2, so you get one that is in between. Despite the fact that there are therefore an infinite number of them, they turn out to be in one-to-one correspondence with integers, with natural numbers. Okay, so very roughly speaking, natural numbers to natural to ratios, fractions to what are called algebraic. So these are rationals, that's what I was looking for, rationals to irrationals which form in two classes. One class is called the algebraic irrationals. So these are your square root 2 and 3 plus square root 5 or whatever. Because these can all occur as solutions of polynomials with integer coefficients. The polynomial should not have arbitrary real numbers as coefficients, and if they have any rational coefficients, you can always convert them to integers by multiplying out by their LCM. So these are solutions of so-called integer polynomials. It turns out that the fractions plus the algebraic irrationals are all countable. So I will leave some space here. And write over here countable and sorry, I meant to say denumerable. So this is finite number elements. A set is countable if it has finite number of elements, 5, 15, 59,000, all countable. Denumerable means in one-to-one correspondence with naturals. So indefinitely large, but you can put them into one-to-one correspondence with natural numbers. The funny property of denumerables is that their proper subsets can be in one-to-one correspondence with them. Usually proper subset means you leave out some elements, then you can never create a one-to-one correspondence in any finite set. But a denumerable set, 1 to infinity, well, you can leave out the first 3 elements and start counting 4 as first, 5 as second. Again you have a one-to-one correspondence with the original set. So that is the strange property of denumerables, but they are still under control in the sense that they are listable as natural numbers. All the odd integers, all the integers that are multiple of 3. So these are all subsets. They are proper subsets, but they are in one-to-one correspondence with the original set. This is called denumerable. And the algebraic irrationals as well as the Qs, the rationals, are all denumerable. This is an amazing result, but that is true. So up to here, but then there still remain funny creatures called transcendentals. The most common examples are pi and e, the base of natural log, and all the other examples of transcendentals would come only from values of special functions like your Bessel functions, and when you define all kinds of functions that can map out the whole space of reals, you will find this next category of irrationals which are not solutions of algebraic equations, but they are solutions of some different, they are values of solutions of differential equations. They will occur in the list of values of, I shouldn't say list, but whatever, in the set of, solution set of and in fact those functions are therefore called transcendental functions sometimes. Turns out that the real line's real weight, its real content is all transcendentals, okay, because all these are countables and you can define a way of giving weightage to an interval such that all the countables, all the denumerables have 0 weight, but then the real line still has, the interval 0 to 1 still has a weightage 1, and that weightage comes entirely from the transcendentals. So funny as it may sound, this is how the continuum is defined. The most important property of the fractions relative to the two irrationals together is that the rationals are dense in reals. So then we defined, so to understand the relation between these two classes of numbers, we needed to define, we did this last time, metric spaces, so that there is a sense of distance between two elements, and then the Cauchy criterion, Cauchy convergence. So just think of the interval between 0 and 1, and it is a metric space because you can define a distance between them is a subtraction of one from the other, the greater from the smaller, and the Cauchy convergence means that the limit point, a sequence is convergent in the Cauchy sense if the difference between the sufficiently far away parts of the series are all close together, and then we say that a space is compact so Cauchy convergence does not necessarily mean the limit point belongs to the same set. All it means that the limit exists. Okay. Limit points. That is the main content of Cauchy sequence, but limit point need not belong to the set. So let us keep this below, and the classic example of this is you can get pi, you can get E as sequences of rationals. You can obtain them in the limit point. I mean, like pi we say is 22/7 is the first approximation, and then you can keep growing the fraction until it approaches pi as well as you like, but pi itself is not a rational. So for example, transcendentals and all irrationals can be obtained as limit points of sequences of rationals. So the limit point need not be itself a rational, but it exists. What we do now is that we include all the limit points. Take a set, consider all Cauchy sequences, and whatever the limit points of all the Cauchy sequences are, include them in the original set. That set is called Cauchy complete. Okay. So just to think back a little bit, what we have done is, well, when you talk about limit, again you are talking of infinite things, but they are denumerable. The sequence is has a denumerable number of terms in it. So we are trying to grasp the non-denumerables by some well-defined logical processes of denumerables, and that is the great achievement of this whole exercise. And after that, the important thing is that the rationals are dense within reals. Every single real number can always be obtained as a limit point. What one can be sure of is that there is nothing else left out. Okay, so I will not spend more time on this. You can read the notes. But this is really the underlying logic. This is all the legal fine print behind everything else that we discuss later. And if there are, you can, I mean, don't be surprised that every once in a while there will be some exceptional case that will be thrown up. And this is why people have tried to plug all these logical holes. And you never know, you may still come out with something new. And when you do, you have something to go back to check whether all the previous reasoning led to that or not, or you have something completely new. So now we write down finally the idea of compactness. It is closed in Cauchy sense. So it obviously has a metric. So is a metric space. Closed in Cauchy sense. And 2, all its elements are bounded. One way to say it is that given any 2 elements, the D, the metric that is existing, DAB, is always less than or equal to some m. The distance between them is bounded to remain, ensured to remain less than some m for all A and B belonging to the set, and for m some real number. So such a set is compact. One classic example is the disk. Let us say in the plane, the disk is compact, whereas the plane itself is not compact. the unit disk with, what shall we say, x squared plus y squared less than or equal to 1 is compact. Okay. Now we come to classical groups, the continuous groups. Finally, with all this preparation, we come to what are called classical groups. This nomenclature is due to Hermann Weyl and Eugene Wigner. So Wigner has, I think Wigner has a book called Group Theory and Applications to Quantum Mechanics. He was the first person to write out the whole book. So as you may know, Heisenberg, who proposed the matrix mechanics, didn't know matrices until after he proposed them. So physicists' education of mathematics did not include matrices in 1920s. So you can imagine that group theory was far from part of that education. And so physicists continued to be surprised all the time how smart mathematicians were, because when they got to a problem and they found the method of calculating, they found that mathematicians already had developed the detailed mathematics of it. So that happened to Wigner and Weyl also. Weyl was himself a mathematician, but Wigner found that everything he needed to do had been done 50 years before. And so Wigner later wrote an article called The Unreasonable Applicability of Mathematics to Physics. And so we are doing this course because of this very unreasonable applicability of group theory to a lot of physics. So they call these groups classical. You will understand in what sense. The other terminology for it is matrix groups. So we begin by talking about matrix groups. What do we mean by this? Take n by n matrices and consider them as group elements, as a group. Set of n by n. Let us begin with real matrices. Under multiplication, usual matrix multiplication, they form a group provided what? We need 4 properties. Closure, we know product of any matrix is a matrix. We know the matrix product is associative, so that is not a problem. The identity matrix exists, all you have to put 1 on the diagonals, but we also need the inverse. So if the matrix is 0 rank, if its determinant is 0, then you can't invert it. So you need to put the condition that determinant of A is not equal to 0. So it is obvious that this set forms a group. The set of all real n by n matrices that are invertible forms a group in the usual sense. And this is going to be our prime and essentially the entire example of what continuous groups are. The only continuous groups we will discuss are all the matrix groups. So there is always a very clear quote realization. Remember, we kept talking in group theory about carrier space and a realization of the group. In the continuous group theory, we are primarily going to talk entirely through the realization itself. But if you go to all the sophisticated mathematics book, they say that there is life beyond that. There are continuous groups that are not necessarily matrix groups. But we are not going to really have to deal with them, and that is why we are going to swear by Weil and Wigner and live with the classical matrix groups. So, to begin with, let us next say, so we already said we are going to talk about the continuous groups entirely in terms of the realization, which is as matrices. The carrier space is the n-dimensional vectors. In matrix representation, column vectors. So that is going to be the carrier space. The group that we identified, the most general group, is called therefore general linear group. And I talked about the carrier space because that makes it clear why we are calling it general and linear. General means they are all the possible matrices that have determinant not equal to 0, and they are essentially linear transformations on this carrier space. Similarly, you can do the same exercise with complex numbers, introduce complex n-dimensional vectors as carrier space, complex n by n matrices whose determinant is not 0, and those are called GL and C. All the classical groups that Weil and Wigner introduce are going to be subgroups of these GLNR or GLNC. Where GL NR is itself a subgroup of GL and C by setting the imaginary parts to 0. So it doesn't matter. Okay. Now let us begin with one of the classical group, which is the orthogonal groups. Okay. And to discuss so the most common classical groups are the orthogonal and unitary groups. Since you already would be familiar with this in some ways, we drop the words, but now we develop formally what this means. We begin with the idea of inner products. So you will see all your familiar things as we go along, familiar ideas as we go along. Remember that, so anyway we'll come to it. Orthogonal meant O transpose O equal to 1, and why that is an interesting property to impose. We go through this little formality. So we say that inner product x y with x and y belonging to n dimensional real vector space should have property of course x y should belong to, that is the 0th property, should give a real number, but more importantly, so what I mean is it's not a property, so it's part of the definition. So inner product is a operation that takes two elements of the carrier space and maps them into a real number. Property 1, it is symmetric. So you will see a analogy to the metric spaces we had defined. This essentially is like defining distance d between 2 points in a metric space. There are of course analogies. The d essentially will turn out to be the distance between end points of your stick vectors. Number 2 is symmetric, bilinear and positive definite. So bilinear is where metric space is a property metric space doesn't have. In metric space we simply said the Schwarz inequality, the triangle inequality. It's actually the triangle inequality in the more general sense is called Schwarz inequality. So the second property is bilinear, which is saying x plus ay plus bw equal to a times xy plus b times xw. So this is called bilinear. We showed here the linearity. So a and b are real numbers because you have a vector space. Vector space is where you can multiply by real numbers. So a and b are real. This property is called bilinearity because what we wrote out is linearity in the second slot, but the property 1 says you can flip it around, so it must also apply to the first slot. So you have bilinearity. And 3 is positive definiteness. Which is that x, if you put the same thing into the bilinear function, this has to be greater than or equal to 0 and 0 only if x is the 0 vector. That is real number 0, this is vector 0. So, these are things familiar to us about dot product or inner product or scalar product, a dot b, a square plus b square plus 2ab cos theta. But we already have one great counter example to this when we get to special relativity, because the Minkowski inner product fails test number 3. So mathematicians had figured everything out in 19th century, but we had something to give that back to them as a gift. Okay. So something very fundamental to physics, but which fails their criterion number 3. So some of the theorems they proved assuming these 3 will fail. Well, notable exception, Minkowski metric. X equal to x0, x1, x2, x3 and x dot y equal to x0, y0 but minus x dot y. And we have set c equal to 1. Usually x0 is c times t. But we know that the Lorentz invariant inner product of 4 vectors has this relative minus sign. So it is not positive definite. So fails criterion 3. But it turns out that still a lot of the things work okay as far as the group itself is concerned. But we do get interesting things when we get to group representations, and we will see some of that in subsequent lectures. On the other hand, so next thing is the complex version. Inner product where the X belongs to n dimensional complex vector space and in this case the multiplication, the scalar multiplication is also by complex numbers. So that is the main difference when we get to complex vector spaces.